Welcome everyone. We are Anmol Agrawal, Vanshika Srivastav and Sayan Chaudhary. Today we will be presenting on Networkit, which is a high performance network analysis tool. Our presentation will cover what network science is, why Networkit is needed, its architecture, feature and applications. Let's begin with some background. So, what is network science? Network science is the study of complex systems represented as networks. In simple terms, a network consists of nodes, which represent entities such as people, computer, or proteins; edges, which represents relationship or interaction between them. Examples include social media networks, internet and communication networks, biological and brain networks. Network science focus on understanding the structure of networks, their behavior and dynamics, and how information or influence flow through them. It combines ideas from graph theory, computer science, physics, and data science. Now coming to the tool, we are focusing on Networkit. Networkit is a network analysis library, not a visualization tool. It is mainly used in domains like social network analysis, communication and computer networks, biological and brain networks, web and information networks. The target users are researchers, data scientists, and students who work with large-scale networks. Introduction to Networkit. Networkit is an open source toolkit designed for large-scale network analysis. Unlike basic tools, Networkit can handle networks with millions or even billions of edges. It combines the simplicity of Python with the performance of C++. This makes it very suitable for research and real-world large data problems. Networkit is developed by researchers specifically for high-performance network science. Now, coming to the significance in network science. Traditional tools like NetworkX are easy to use but struggle with very large graphs. Modern networks such as social media or internet graphs are huge and complex. Networkit solve these problems by providing faster computations, parallel processing, scalable graph analytics. Because of this, Networkit is widely used in academic research and industry-level data analytics. Now, coming to the architecture and design of Networkit. Networkit follows a hybrid architecture. At the top, it has a Python front end which make it easy to use. Underneath, there is a C++ backend which ensures high performance. The algorithms are parallelized using OpenMP so they can efficiently use multi-core processors. It also has modular design, meaning components are well separated and easy to extend. This slide shows a high-level architecture of Networkit. On the user side, we interact with Networkit using the Python APIs, and internally The heavy computations are done in the C++ core engine. Algorithms run in parallel, improving speed. Memory-efficient data structures are used to handle large graphs. This design allows Networkit to be both user-friendly and extremely fast. Now, coming to the integration with Python ecosystem, Networkit integrates very well with the Python data science ecosystem. It works seamlessly with NumPy, which is used for numerical computation and efficient array manipulation. It also integrates with SciPy, which supports scientific computing and statistical analysis. For handling and analysis, for handling and analyzing network results, Networkit can be combined with pandas and making data processing easier and more structured. For visualization purpose, matplotlib is commonly used to plot network metrics such as degree distribution and centrality values. Finally, Networkit can be used in Jupyter Notebook, which allows interactive analysis as experimentation. Overall, this integration allows Networkit to fit naturally into standard Python data science workflows. Now, coming to the supported network types, Networkit supports many types of networks, including static graphs, directed and undirected graphs, weighted and unweighted graphs. It is specifically optimized for large-scale sparse networks which are common in real-world data. Both synthetic and real-world data sets can be analyzed using Networkit. Coming to the core functionalities, Networkit provides several core functionalities. First, it supports graph creation and loading for different formats. It includes many centrality measures such as degree, betweenness, closeness, PageRank. It also supports some major advanced graphs like community detection, connectivity analysis, finding connected components. The image on the right side represents these analytical capabilities visually. Now, before deep diving to the network kit core functionalities and experimentation, there are some basic centrality measures key definitions for a better understanding of network science. First is degree centrality. It measures the number of direct connections a node has. A node with high degree centrality is locally important or very active. For example, in a social network, this could represent a person with many friends. Next is betweenness centrality. This measures how often a node lies on the shortest paths between other nodes. Nodes with high betweenness acts as bridges or intermediaries, controlling the flow of information. Such nodes are critical in communication networks, transportation systems, and social networks. Then we have closeness centrality. It is based on the average shortest distance from a node to all other nodes. A node with high closeness can reach all other nodes quickly, meaning it can it can spread information efficiently across the network. Finally, PageRank. PageRank measures node importance based on just on the number of connections. Sorry, not just on the number of connections, but on the importance of the node it is connected to. Being connected to important nodes increase a node's own importance. This algorithm was originally developed by Google to rank web pages. All these centrality measures are efficiently implemented in Networkit even for very large networks. Now, coming to the algorithm supported, Networkit implements many well-known graph algorithms. This includes shortest path algorithm like PFS and Dijkstra, community detection algorithms like Louvain, PLM, connected component analysis. It also provides graph generators such as Ados-Rene and Barabasi-Albert models. These are useful for stimulation and experiments. Now, the installation and setup. Networkit is easy to install and supports Linux, macOS, and Windows also. Installation can be done using a simple Python command like pip install networkit. It can be used in Python scripts, Jupyter Notebook, and some modern application, cloud-based applications like Google Colab. I have included a website of Networkit which shows how to install any in any operating system Networkit and use it. I will quickly show you the website so that you will be always be updated about the commands what you have to use to install. But for we will cover the commands and installation part also in the hands-on session. So here is the official Networkit website, networkit.github.io. You have to click to the Get Started button. Now you can see all the system requirements for installing Networkit in your PC, the installation steps for Linux, installation steps for macOS, and installation steps for Windows. You can easily install this commands in your operating system in your computer, and you can use any ID like Jupyter Notebook or Google Colab to run Networkit commands. Now coming back to the presentation. Scalability and performance. One of the biggest strengths of Networkit is its scalability. It is designed to handle very large networks efficiently. Key features include efficient memory usage, parallel execution, much better performance than NetworkX on large graphs. This make it ideal for performance critical applications. Real world applications. Networkit is used in many real world applications such as social media and network analysis, internet and topology analysis, protein interaction and biological networks, fraud detection and cybersecurity, recommendation systems. Any domain involving large and complex networks can benefit from Networkit. Coming to the strengths, to summarize the strengths, high performance and scalability, parallelized algorithms, simple Python interface, actively maintained and well documented. These features make Networkit a strong choice for large-scale network analysis. Now coming to the limitation part, like any tool, Networkit has some limitations. It has limited built-in visualization support, so external tools are needed. Its ecosystem is smaller compared to NetworkX. Also, understanding advanced features require good knowledge of graph theory. In Networkit, you have some advanced features which you can't directly use before having some prior knowledge. Now, use case over workflow. A typical workflow using Networkit looks like: first, we input a real world or synthetic graph. Then, we process it by loading the graph, computing centrality measures, detecting communities. Finally, we obtain network metrics and analysis results. Now, coming to the hands-on demonstration, the hands-on demonstration will be covered by Sayan and Vanshika, my group partners. In hands-on session, the steps would include installing Networkit, creating or loading a graph, computing centrality measures, detecting communities, and analyzing performance. I have included the user network guide, Networkit user guide, the official user guide of Networkit. They have in their website, which you can always refer for the updated versions and updated commands for Networkit. I will quickly show you the user guide. So this is the Networkit user guide. You can see how to import Networkit as NK. You can see different graph objects, degree distribution, community detection, centrality measures, and more different functionalities which Networkit supports. You can always refer to this documentation for for the latest updates in Networkit. So that's all from my side. Now further presentation will be covered by Sayan and Vanshika. Thank you.
Thank you, Anmol. I am Sanjogri, and now I will demonstrate Networkit practically using Google Colab. We will start by creating a simple, undirected, unweighted graph and then gradually explore different network analysis features provided by Networkit. The idea is to understand not just how to run the code, but also how to interpret the result in terms of graph theory and real world networks. Before we can work with Networkit, we need to install it in the current environment. Since Google Colab already provides a Linux-based system, Networkit can be installed directly using pip without any manual compilation or configuration. For completeness and portability, the installation commands for Windows or Windows subsystem for Linux are also commented in the notebook. This way, the same notebook can be reused outside Colab as well. Pip install Networkit. This command downloads the Networkit library. It also installs all required dependencies, including the optimized C++ backend that Networkit relies on for performance. As you can see, the installation finishes successfully and prints a confirmation message. This tells us that Networkit is now available in the environment, so we can move on to importing and using it. After installation, we need to import the Networkit library so that we can access its graph, data structure, and algorithm. Import Networkit as NK. Import the Networkit package and assign it the short name NK to make the code shorter and cleaner. nk.version print the installed version of Networkit, which help in reproducibility and verification. As you can see, the version number is printed clearly. This confirms that Networkit has been imported correctly and is ready to be used for graph analysis. Every network analysis starts with a graph. Here we create an undirected unweighted graph, which is most basic and commonly used form, especially for introductory analysis and demonstration. Here, first line of code creates a graph with 6 nodes numbered from 0 to 5. Weighted is equal to false indicates that all edges are treated equally. Directed is equal to false indicates that all edges have no direction. G.addEdge u, v. This command adds an undirected edge between node u and v. As you can see, the output confirms that the graph has 6 nodes and 6 edges. This tells us that the graph structure has been created exactly as we intended. Before applying any algorithm, it is important to understand the basic structural properties of the graph. These properties tells us what kind of graph we are dealing with and help us decide which algorithm are applicable. As you can see, the graph is undirected and unweighted, which is matches how we constructed it. The density value of 0.4 means that 40% of all possible edges are present. This indicates that the graph is relatively sparse, which is typical for most real-world networks. Iterating over nodes and edges allow us to explicitly inspect the structure of graph and verify that it matches our expectation. As you can see, all node IDs and edge connection are printed. This confirms that the internal structure of the graph is correct. Degree is the simplest measure of connectivity and tells us how many direct connection each node has. As you can see, node 1 has higher degree than other nodes, meaning it is more connected. Node 5 has the lowest degree, indicating that it lies near the boundary of the network. So far, we have seen degree, which is simply count how many neighbor a node has. However, degree by itself depends on the size of the graph. Degree centrality improves this by normalizing the degree. So the value lie between 0 and 1. This makes it easier to compare nodes importance even across defined graphs. The first line creates a degree centrality object for the graph. Normalized is equal to true ensures that the values are scaled relative to the maximum possible degree. dc.run This command actually computes the degree centrality value for all nodes. You can see the output list along their degree centrality values. A higher value means the node has more direct connection relative to the graph size. For example, node 1 has the highest value, which tells us that it is locally very influential. Nodes with smaller values, such as 5, are less connected. Degree centrality looks only at local connection. Betweenness centrality, on the other hand, looks at the global role of a node. It measures how often a node appears on the shortest path between other nodes. Nodes with higher betweenness often act as bridges or bottleneck in the network. The first line creates a betweenness centrality object. Internally, this algorithm can compute shortest paths between many pair of nodes. bc.run execute the betweenness centrality computation. You can see from the output, node 1 and 3 have the highest betweenness values. This means that many shortest paths pass through these nodes. In practical terms, if those nodes are removed, communication between different parts of the network would be significantly disrupted. Closeness centrality. Closeness centrality measures how close a node is to all other nodes in the network. Instead of focusing on bridges, it focuses on how quickly information can spread from a node. Nodes with higher closeness can reach all other using fewer steps on average. The first line creates a closeness centrality object. The parameters specify how unreachable nodes and normalization are handled. Close.run computes closeness values for all nodes. As you can see, node 1 again has the highest closeness value. This tells us that node 1 can reach other nodes faster than most others. Nodes with lower closeness values are further away from the rest of the network and take more steps to reach everyone. Shortest path algorithms are fundamental in network analysis. Since our graph is unweighted, breadth first search is most appropriate and efficient algorithm. BFS computes the shortest path in terms of number of edges. First line initialize BFS starting from node 0. BFS.run executes the BFS traversal. BFS.distance I returns the shortest distance from node 0 to node I. Each node is assigned a distance value. A distance of 0 means the node is the source itself. Larger value indicates nodes that are further away. For example, node 5 has a distance of 4, meaning it takes 4 edges to reach 5 from node 0. Now we move from node to node distance to graph-wide distance measure. Eccentricity tells us how far a node is from the farthest node in the graph. Radius help us identify the most central position in the entire network. As you can see, an eccentricity output like 5, 4 has two parts. The first value 5 is the ID of the farthest node. The second value 4 is the distance to that farthest node. This means that the maximum distance from this node to any other node is 4 edges. The radius value represents the smallest eccentricity among all nodes, meaning it corresponds to the most centrality located node in the graph. While radius focus on the most central node, diameter focus on the most distant node. It tells us how large the graph is in terms of shortest path distance. You can see a diameter value 4 means the longest shortest path between any two nodes in the graph is 4 edges. This gives us an overall idea how spread out the network is. So far, our graph has been fully connected. To demonstrate connectivity-based algorithm, we now intentionally modify the same graph by adding another cluster. This helps us clearly see how Networkit handles disconnected graphs. As you can see, the number of nodes and edges increases. This confirms that the new cluster has been added and the graph is no longer fully connected. Connected components help us identify group of nodes where each node is reachable from every other node in the same group. The output shows two connected components. One component contains 6 nodes and the other contains 4 nodes. This clearly confirms that the graph has become disconnected. In real-world analysis, many algorithms assume the graph is connected. Therefore, it is common practice to focus on the largest connected component. You can see the largest connected component contains 6 nodes and 6 edges. This corresponds to the original part of the graph before the second cluster was added. The clustering coefficient measures how tightly a node's neighbors are connected to each other. It helps us understand local group formation. A clustering coefficient of 1 means all neighbors of a node connected forming a clique. A value of 0 means none of its neighbors are connected. Intermediate values indicate partial connectivity among neighbors. Community detection aims to identify groups of nodes that are more densely connected internally than externally. As you can see, different nodes are assigned different community IDs. Nodes with same ID belong to the same community, indicating tightly connected groups within the graph. Far, we have been working with a small graph to clearly understand how each algorithm works. However, Networkit is specifically designed for large-scale network analysis. To demonstrate this capability, we now generate a larger synthetic graph using a standard random graph model. This helps us to understand how Networkit behaves when the graph size increases. The first line creates a generator based on the Eidos-Renyi random graph model. 100 specifies the number of nodes. 0.05 specifies the probability of an edge between any pair of nodes. Gen.generate. This command actually generates the graph using the given parameter. rg.number of nodes return the total number of nodes in the generated graph. rg.number of edges returns the total number of edges created randomly. You can see the output shows the number of nodes and edges in the generated graph. The number of nodes is exactly 100, which matches our input parameter. The number of edges is determined by the edge probability, so it may vary slightly each time the code is run. This confirms that we have successfully created a larger random graph for further analysis. After generating a large graph, one of the first structural properties we usually analyze is connectivity. In random graph, it is not guaranteed that all nodes are connected, especially when the edge probability is low. Therefore, we check how many connected components are there and how nodes are distributed among them. First line initialize the connected components algorithm for the graph RJ. cc large.run. This command computes all connected components in the graph. cc large.number of components return the total number of connected components. cc large.get component sizes return a dictionary where each key is a component ID and each value is the size of the component. As you can see, the number of components is printed first. In this case, the output shows one connected component, which means the entire graph is connected. This is expected because at an edge probability of 0.05, Edo-Sreni graph often form a single large connected component. These component sizes output confirm this by showing that all nodes belong to one component. This result tells us the graph has a giant component, which is a common phenomenon in random graph theory. Instead of looking individual nodes, we now analyze the overall degree distribution of the large graph. Degree statistics help us understand how connections are spread across the network, whether the graph contains highly connected nodes or mostly low degree nodes. rg.iter nodes iterates over all nodes in the graph. rg.degree u returns the degree of node u. As you can see, the minimum degree shows how many connections the least connected node has. The maximum degree highlights the most highly connected node in the graph. The average degree gives us a general idea how dense the network is overall. In random graphs, most nodes tend to have degree close to the average, with fewer nodes having very high or very low degree. These statistics help us understand the structural characteristic of the network without examining each node individually. With this, we have seen how Networkit efficiently handles larger graphs and provides meaningful structural insight even at scale. Thank you.
Thank you, Saran, for this hands-on demonstration. In this final segment, I will demonstrate a complete hands-on workflow using Networkit. I will walk through how to generate networks, analyze their structure, compute centrality measures, detect communities, and evaluate performance. Along the way, I will explain not just what each algorithm does, but also why it is used and how to interpret the outputs in real-world research. Network science is about understanding how complex systems are connected and how those connections influence behavior. Networkit helps transform these connections into measurable insights. Let us begin by setting up our environment. We start by installing and importing required libraries. We install Networkit, which is the main computational engine used for network analysis. It is implemented in C++ but provides Python bindings, making it both fast and easy to use. Next, we import matplotlib. This library helps visualize network properties such as distributions and connectivity patterns. We also import NetworkX. While NetworkIt focuses on performance, NetworkX is useful for visualization and graph drawing. Then we import pandas, which allows us to convert network matrices into structured data for machine learning or statistical analysis. Finally, we import the time module. This allows us to measure algorithm performance. This setup creates a complete analytical pipeline that combines fast computation, visualization, and data science integration. Now, we generate two types of networks: Erdos-Rene random network and the Barabasi-Albert scale-free network. The Erdos-Rene model creates edges randomly between nodes based on probability. This produces uniform and random connectivity. The Barabasi-Albert model uses preferential attachment. This means new nodes prefer connecting to already well-connected nodes. This produces hubs. Now let us analyze the output of this code cell. For the Erdos-Renyi graph, we observe 100 nodes and 270 edges. The density is approximately 0.054. Density measures how full the network is. A low value indicates sparsity. The clustering coefficient is about 0.03. This means very few triangles or tightly connected groups exist. Random graphs rarely form communities. The maximum degree is 12. This means no node dominates connectivity. There is single connected component, that means there are no fragments in the graph. For the Barabasi-Albert graph, we see there are 100 nodes but 294 edges. The clustering coefficient is 0.14, which is significantly higher. This indicates stronger local group formation. The maximum degree is 31. This reveals the presence of a hub node with many connections. The network has only one connected component, meaning the entire system is structurally unified. Why is this step done? Researchers compare theoretical models to understand how connection rules influence structure. Scale-free networks resemble real-world systems, such as social media and transportation networks. Next, we choose the Barabasi-Albert network for deeper analysis because it better represents real systems. Networkit graphs are converted into Network-X format using an adapter. This allows us to visualize the network using drawing tools. The visualization shows a dense central region with several nodes radiating outwards. These central nodes represent hubs that dominate connectivity. Why does visualization matter? Visualization helps researchers build intuition before performing mathematical analysis. It allows quick identification of structural patterns like hubs and clusters. Let's move on to the degree distribution. Degree distribution measures how connections are distributed across nodes. It reveals whether connectivity is evenly distributed or dominated by hubs. This plot shows a heavy-tailed distribution. Most nodes have few connections, while a few nodes have very high connections. This confirms scale-free behavior. Why is this analysis important? Degree distribution helps identify network resilience. If hub node fails, the network can collapse quickly. This insight is critical in cybersecurity and infrastructure design. Let's move on to this hop plot. The hop plot measures how quickly nodes become reachable as the number of steps increases. The steep curve indicates that most nodes become reachable within a few steps. This confirms small world behavior. Small world networks allow rapid information spread. This explains viral content propagation in social networks. Connected components are groups of nodes that can reach each other through paths. Our plot here shows that 100% of the nodes belong to a single component. There are no isolated fragments. Many algorithms assume connectivity. Confirming connectivity ensures meaningful analysis. Now let's move on to the centrality measures of this graph. At first we look at the page rank. Page rank measures node prestige based on connections from other important nodes. Node 2 has the highest page rank score of approximately 0.046. This means it is the most influential node in terms of receiving attention. Next comes the betweenness centrality. Betweenness measures how often a node less lies on shortest paths between other nodes. Node 2 again ranks highest. This indicates it acts as a communication bridge controlling information flow. Next is the closeness centrality. Closeness measures how quickly a node can reach others. Node 2 has the highest closeness value, meaning it can spread information fastest. The next is degree centrality. Degree centrality measures direct connectivity. Node 2 has 31 connections, confirming that it is a hub. Why is the centrality important? Centrality identifies influencers, vulnerabilities, and key actors in networks. Let's move on to the K-core decomposition. K-core decomposition identifies structural layers by removing weakly connected nodes. All nodes belong to at least a 3 core. This means each node is connected to at least 3 other core members, indicating strong structural stability. K-core analysis helps identify the backbone of a network that remains connected under stress. Here we are extracting largest connected component. We isolate the largest functional part of the network. The properties remain unchanged, confirming the network was fully connected. Researchers often focus only on the giant component to avoid distortions from isolated fragments, which we do not have in our case. Next is community detection. Community detection identifies dense clusters within networks. This algorithm detects 9 communities. This indicates the network contains modular substructures. Why do communities matter? Communities represent social groups, functional modules, or biological clusters. We have also calculated modularity here. Modularity measures how strong community divisions are. The modularity value here is 0.34, which indicates meaningful cluster separation rather than random grouping. Next, we will calculate the diameter. Diameter measures the longest, shortest path between nodes. The diameter is 4. This means that even the two most distant nodes are only 4 steps apart. Diameter measures network navigability and efficiency. Here comes the clustering coefficient. Clustering measures triangle density among neighbors. Some nodes have clustering values around 0.67. This means two-thirds of their neighbors are connected to each other, forming tightly knit groups. Here we are taking a weighted graph example. Weighted edges represent strength or cost of relationships. The assigned weight of 3.5 confirms successful conversion to weighted representation. Why weighted graphs are used? They model realistic systems like transportation cost or communication strengths. Next, we are calculating the performance benchmark, which is a very crucial functionality that Networkit offers. We measure BFS runtime to evaluate computational efficiency. Execution time is approximately 0.0003 seconds. This demonstrates Networkit's high performance and scalability. Performance does matter because large real-world networks contain millions of nodes. Efficient computation enables practical research. At last, we are exporting every detail about the graph to pandas. Network matrices are converted into structured datasets. The table shows PageRank scores for nodes. This allows integration with machine learning pipelines. Let's discuss the limitations of Networkit. While Networkit excels in performance, it provides limited visualization tools and requires knowledge of graph theory also. However, its scalability makes it ideal for research level analysis. Let's also discuss some real world applications of Networkit. Networkit techniques are used in cybersecurity, fraud detection, epidemiology, transportation optimization, social influence analysis, and many more things. To conclude, Networkit provides a powerful and scalable platform for analyzing large complex networks. Through this demonstration, we explored how network structure influences communication, stability, and influence. We analyzed connectivity, identified influential nodes, detected communities, and evaluated performance. Network science allows us to transform complex systems into understandable patterns. Networkit makes this transformation computationally efficient and research ready. Thank you for watching our presentation. We truly appreciate your time and attention. We would be happy to answer any questions.